Today's stream is about to start. We'll talk about code or whatever we'll talk about today. It's about to start, so please hang tight while I check that everything is okay. Sound check, camera check, lights check. How's my hair? Oh, wait, I don't have any hair. Maybe put some pants on and I am good to go. So get ready wherever you are, 'cause this stream is about to start. Get ready wherever you are, 'cause this stream is about to start. Hi, I'm Leonard Facchinetti, and let's write some code together, shall we? What we have on the menu today is circular buffers. We are circling back to that, and we are doing that to continue our library for JS effects. That this library is going to help you develop real-time audio effects in Reaper. It comes with a design system. We already finished that, and we are working our way porting some material from a previous version of the library that I was not completely happy with. It was too slow and clunky. We are changing how things work. And I implemented this notion of circular counter, which is something that I extracted from the component that was drawing waveforms. And we did this yesterday. I'm not so happy with the result of this, of our code yesterday. So I'm going to start by changing the way that this code works, and then we are going to move on to circular buffers. And a circular counter, the thing that we are going to revisit now, has the purpose of, it's modulo arithmetic. It's just going to count, for instance, from 0 up to 3, and then from 0 up to 3 again and again. And that can be useful for things like when you have some block of code that you only want to run every 3 samples or every 256 samples, something like that. It can also be useful for things like a circular buffer, which is just a chunk of memory that you access circularly. So when you get to the end, you return to the beginning as if the end and the beginning were connected. The purpose of a circular buffer is to store samples with a delay, and you can also use that to store a waveform, to show the waveform. So circular counters are super important, they're super useful, and they are used all over the place, so it means that they need to be as fast as they can be. And this implementation is not so fast, and that's the first concern that I have, the first thing that makes me unsatisfied with this implementation. The second is that the way it works, actually, the way you use the thing. So the way you use the thing right now is you allocate this circular counter data structure, and you have to pass all the parameters there. So you have to say what is the initial step, or the initial value, the final value, the steps. So if you're counting from 0 to 3, you have to specify all of this here. And typically you would do that in the init block. As your effect is loaded, you would configure a circular counter like this. But then you would use the circular counter elsewhere, like when you're drawing waveforms, you're going to use that in the GFX block, or when you're processing samples, you're going to use that way below. So there is this disconnect between the configuration of the circular counter and the use of the circular counter. And as much as it's possible, I prefer to co-locate things that are related. So 2 things that I don't like. Too many memory accesses, it's going to be slow. And I guess one is a consequence of the other. There is this disconnect between where I set the parameters for the circular counter and where I will use the circular counter. So I think there is a way for us to fix both of these issues at once. So I guess let's start with the test, and then we can look at the implementation. Yeah, let's start with the test, because one of my main concerns is how you use this thing. So I think that the way I want to use this thing is just you will be responsible for holding on to the value of the circular counter. So currently the counter itself, the count, is part of this data structure. But I'm going to try to extract this. Yeah, this is going to work out. So the count itself, this guy, is no longer going to be part of the data structure. The from, the to, the step, these three are concerns of the setup here. So these are the parts that I want to have near where the circular counter is incremented. So I guess a circular counter or circular count, yeah, something like this. It's going to start at 0, and then I will have something that will do the stepping of the circular counter. So I guess I will call this the circular counter. And then I had to give the range, so from 0 to 3, and a step in steps of 1. Oh, and you know what? This may be a perfect situation for us to use default values. But yeah, all right, I will do that in a moment. So when I say that you will be responsible for keeping the circular counter, it means that this function is going to return a new value for the circular counter. So this function, we don't need a data structure, we don't need any sort of object to hold this value, because there is only one value that we care about, which is this one. All the rest of them are parameters. So now this will be near where you use the circular counter. And then you don't need to store these values in the data structure, which means that there is no need for a data structure, which makes everything faster. Win, win, win. Awesome. So I guess I am going to remove a lot of this code, but for now I'll just comment things out. Or maybe not comment out, I will put them in a separate buffer just so that the code here is cleaner. So one trick that you can do in languages like C, and that you can do in JSFX as well, is you can assign to multiple variables at once. So the value of this will be assigned to the circular counter as well as to the variable A. I am instead going to call this the circular counter 0, and this will be circular counter 1, for instance. Or maybe I can already put this in the test. Yeah, so the test starts by asserting that the circular counter is 0. That's kind of silly, I don't have to do that. Then I can do an assignment and a check at once. Single line does both. So this is going to update the circular counter, and it's going to check that now the value should be 1. But I said that I wanted to start using function overloading, which is, or default values, however you want to think about this, which is kind of a neat feature that I didn't know was a thing until I was reading Geraint Love's code. Here on the stream, we were looking for examples of drawing to different buffers, and I saw something like that. So I think it's possible for me to do something like this, where I have the all values for the initial and the step, and I just have to give the circular counter and the length. So with just this, I can get rid of most of this code. I'll put it in the same buffer as the other one. And then let's do the circular counting situation here, which will be a function with circular counter. And this will be the circular counter, and this will be 2. So this is the value that goes up to. And then all I got to do is take the circular counter, add 1. This is the default step, step 1. Then I will check if the circular counter is equal to the 2 value, then circular counter minus equal 2, and return the circular counter this way. Great. So this is the simplest example, but I think this is already working. And it is. So next, let's have an example of having a start value, just like this. And I expect this to be 2. So now let's have an implementation where we have a start value, and now I have to remember if I want to put the overloaded function first or second. I don't need to look at that code by Gerard Love anymore. We know that in order to be able to call a function, it needs to appear before you in JSFX. You can only call functions that have been defined before you. So the version that is complete with circular counter as well as from and to, that version needs to appear before. And then this can just call that with a default value of from being 0. And then this is going to be not that, but 2 minus from. And then I think that this is still working. And it is. Next, let's have a version where we pass this step. And then I expect this to be 0. So the version with this step, well, we need to take another argument here, which is this step. And then this one will have a default step hanging there. Probably want to have a function that looks like this. And I need to pass the from along. Okay, so that's the simplest version, the one that we tested first. And this one calls that one with the default from. And then this one calls that one, which is the complete version with from, to, and step. So in other words, the signature of this function is it returns the counter and but the from is optional. The to is not optional. And the step is optional as well. And here I'm sort of using TypeScript notation for types, but I think I'd rather use C notation for types. Okay. So if I call the function with just 2 arguments, it's this invocation. And then there is this optional argument in the middle, which is sort of unusual, but it reads better. And then it's this version that calls to the other version. Okay, all of that makes sense. So now let's test this. See if it's still working. And it is. I guess next we have to test the notion of fractional counting. I'm thinking if I want to do negative counting as well. I don't think that's super useful. I cannot think of a use for that. And it complicates this code. I have to add a check if the step is negative. I don't think I want to do that. So I'll just keep this all positive values. All of these are positive values. I'll just say positive number. Something like that. It's just for it's documentation of sorts. So just have to deal with this actually. If I only have positive steps, I think that this is going to work. So let's try this again. Or actually, let's test this. So if I take the circular counter and I go in steps of like 1.7, then it should be 1.7, and 1.7 plus 1.7 is going to be 3.4, so I expect this to wrap around and be 0.4. Or rather, how about we do from 1 to 3? Because then it's supposed to be, it goes from 0 plus 1.7 should be 1.7, but then 1.7 plus that will be 0.4, and then if we start counting at 1, it should be 1.4. In this way, in this clever little trick, we are testing all the branches of this function, I think. And it's still passing. Great. So this implementation, I think, reads much better. And then it's your responsibility to track the circular counter, and it's your responsibility to check if you wrapped around. So you just start at 0, and then if it's 0, then you run some block of code. And this, I think, simplifies all of this that we wrote yesterday. And it doesn't use the memory, so it's faster too. And the code is easier to make sense of and everything. And we don't have to check. It's not as powerful. We're not letting negative steps occur here, but I think worst comes to worst, if you need negative steps, you can always use positive steps and negate the circular counter when you're using it. So it will be fine. And then I think that wraps up what I wanted to do with the circular counter. So let's move on to the circular buffer. And the circular buffer, as I said, we already implemented the circular buffer, but there are some things that are lacking on the circular buffer that we implemented before. The main thing that is lacking is the notion of multiple buffers at once. What we had before was a singular circular buffer, and if you wanted multiple circular buffers, you would have to instantiate the data structure over and over. But I was noticing that every time I was going to use the circular buffer, I was doing something like one circular buffer per channel of audio. Or in any case, there were multiple circular buffers. So instead, this time, what we are going to do is implement the idea of multi-channel circular buffers. And the reason why I care about this is that, again, I think it will make things faster because we'll not keep as many circular counters in memory. And it will be simpler to use as well, because let me show you some code from the old version of the library. Yeah, it looked like this. So here I'm using a circular buffer, and what I have to do is declare a bunch of circular buffers. It's an array of circular buffers, one per channel. And then I have to loop, and I have to instantiate one circular buffer per channel. And you can see this pattern in many situations here. So what I want to do is to have this notion of circular buffer that is multi-channel. And I want to play around with this abstraction, with this concept, and see if we like it. I think there will be some ways for us to optimize some stuff in the implementation, make things faster, potentially make them easier to use. So a circular buffer will have to be a data structure. And I think that what we can do is use a similar trick to what we used in arrays to store the size of the circular buffer in the negative indices. Yeah, I think that will be a nice trick. So I will store the size of the circular buffer in position -1. And I will store, I wonder if I should call them channels. How about we start with a singular circular buffer, just like the one we had, and then we extend it to be multi-channel. Because maybe you will want to have some circular buffer that is not multi-channel. No, let's just bite the bullet. Circular buffer channels will be stored in position -2. Okay, and then a function that will create these circular buffers. I will need to allocate memory here. And I will need to allocate 2 positions for these 2 pieces of data, plus size times the number of channels. I'm going to write this the other way around. Yeah, I want the layout of the memory to be the circular buffer per channel aligned like this. So channel 0 will have a size, channel 1 will have a size. So we are first going to index into the channel and then into the size of the circular buffer, the exact position you want to have. And I also need another piece of data, which is the current position. Let me just double check that this is the trick I used in arrays. Yes. Perfect. Great. So okay. Size, the number of channels, and the position. And then this +3 situation is kind of interesting. It's pointer arithmetic. Great stuff. So now let's store and the position is going to start at 0. And then I return the circular buffer. And then I need a function to store data into the circular buffer. So I'll call this circular buffer set given a circular buffer. And this is a case in which I think it makes sense to declare a data structure that will hold some information in the init block. Unlike the circular counter, I think this warrants allocation in the init block because it has to do with memory. Circular buffer is all about a buffer. It's all about memory. And then it makes sense to store this in a data structure like this. So I'll take the circular buffer. I will take the channel, and I will take the value. And then simply what I'm going to do is take the circular buffer, and I need to get its size. So I'll have a local variable here called size, and I will do a line that looks like this. Then I am going to compute the position where I need to set this value. So it will be circular buffer. At a certain position, we'll get the value. The position will be size times channel plus, I also need this position, don't I? Yeah. So let's do a line that looks like this. Just like that. And again, pointer arithmetic. This code is harder to read than the code we were writing before. At least harder to read is something debatable. I find pointer arithmetic generally hard to read because the notion of how the layout of the memory even works it's only in your head. But at the same time, the code is much shorter, so it may be actually easier to read, so who knows. Okay, so that's to set a value. I also need a function to advance the pointer. And this one is, I wanted to return the circular buffer itself. No, I won't care about what it returns. But let's think about what it needs to do. It needs to update the position. So I will have a local variable here called position. I'll start by getting the current position. Then I will do position, and then I will use the circular counter. And what is the 2? The 2 is the size. And then I need to store this. So I'll do a line that looks like this, but reversed. Great. And it also has the side effect of returning the new position, but you shouldn't rely on that. Then I put new lines here. I'm not doing that anywhere else, so I think it's better this way. Oh, and because I am now using function overloading, I can very easily implement a version here that takes only the size. So if you want to pretend that you have a circular buffer with a single channel, you can just use this function. Similarly, I can do that here. If you don't want to use a channel, that's fine. I'll use this version with channel 0. Buffer advance is the same. Then I will need to get values eventually. And I need to pass the channel and a given offset. And I'm going to already implement the overloaded version of this because it's so simple. Then this I will need to get from the circular buffer the size. Well, it will be similar to this, except that I'm not setting the value, I am getting something. But the issue here is the offset. Yeah, let's do position minus equal offset. And then let's check if position is less than 0, then position plus equals size. Okay, I think that does it. Yikes, that was a lot of code. That was a lot of code that we wrote somewhat fast, and there are no tests. So let's test this step by step. And this whole thing that I'm doing here is sort of something that I think I would like to extract into its own function. So let's extract this into its own function and then we'll test that separately because it will be easier that way. So it's similar to this notion of circular counting, and circular counting is not even a data structure anymore. So I think it belongs up here. Yeah, it's closer to map. And what if instead of circular counting, we call this wrapping, because that's what it does. No, I think we need a different notion of wrapping. We need to extract a notion of wrapping that maybe the circular counter can use. Yeah, so let's take the tangent on the tangent and implement wrap. And I don't have that already. Okay. So I'll take a value, minimum, maximum. Yeah. Okay, yeah, I think that makes sense. And if the value is less than the minimum, let's do value plus equals the difference between the maximum and the minimum. And in the end, we want to return the value. And if it's greater than or equal to the maximum, we just subtract that amount. Let's write some tests for wrap right next to map. And we'll wrap the value 1 between 0 and 2. That should be 1. And if we wrap the number 2 between 0, the number 2 between 0 and 2, I expect that to be 0. And if I try to do 3, I expect that to be 1. Let's have an overloaded version of this. Where we'll wrap with a minimum of 0. I don't really like this notion that you can only call functions that come before you, because then the simpler versions of the functions need to go below. But it is what it is. So now we can remove all these zeros. And I think I will specialize. I don't like how I have to check these two things. It's somewhat slow to do both checks when I know for sure when calling this. In many cases, I know what I want, if I'm going below or if I'm going above. So I will have more functions. A minimum. So it will be a value and a minimum. And it will be this version. Well, I can simplify this further. I can do, if it's less than the minimum, then that. Otherwise, it is the value. I think I'll do this the other way around. And then let's do another one for the maximum. Oh, there is an issue. I don't know the range here, because I'm not passing the maximum. So I guess I'll just take the minimum and the maximum. Boy, this is a lot of work designing this API. Okay. Oh, I need to say value plus the range, just like that. Then let's have another version where the minimum is known. It is 0. Then let's have something similar for maximum. And then this one can depend on the ones above. And this is the one for when you don't know whether you are going below the minimum or above the maximum. So for that one, I can call minimum with the value minimum and maximum, and then I can call the maximum not in love with this, but it will do the job. Yeah, let's review this. Okay, let's write tests for this. We definitely need tests for this. So let's start by testing minimum. So if my value is 1 and I want it to be between 0 and 2, I expect it to be 1 because it's in the range. But if it's below, like -1, then I expect it to be 1 as well. I think so. Let's see. Let's see if these tests are passing. And because these are zeros, you can take them out. They are the default. Okay. Well, the circular counter is still passing, but where is my rep? It's passing. So now let's do the same for the maximum. So if I am between 0 and 2 and I am at 1, I expect the output to be 1. But if I am at 3, I expect the output to be 1 as well. Let's see if this one is working. Rep. It is passing. Great. So now that I have this passing, I don't really need to test the other version because it just depends on the other two ones, but I will. So rep between 0 and 2 with so we have 2 tests for minimum, 1 in the range, 1 outside the range, 2 tests for maximum, 1 in the range, 1 outside the range, 2 tests for rep, 1 below, 1 above. All of this should be passing. First try, you see. And they are passing. First try. Easy stuff. So now that we have a wrapper, we don't need to do this computation by hand. We can just increment this step like this. And we know that we are only ever going above. So I can wrap maximum of circular counter from and to. And is there a value to having this abstraction now that we have rep? I think so. It's such a simple thing, but I think there is value in having this. I think it will read nice on the page when you start using it, and this is more like a low-level utility kind of thing. So I think I changed this implementation, so let's test if the circular counter is still working. It's not. Let's see what's not passing about it. Circular counter. Did I change the position of the tests? Because I put circular counter next to wrap. And I feel like I forgot to do it here. That's just repositioning the test. It's not going to make the tests pass. It's going to still say that the circular counter is failing. And that's the only failing test, right? Right. So let's find the test for the circular counter. Let's set the circular counter to 0. What's the value of the circular counter? It's 0. So when I add 3, or when I add 1, it should be 1. So this is passing. And then, oh, I guess I need to do something like this so that the whole thing executes. Then what is the value of circular counter? It's 1. So far so good. I guess I can do something like this. And this evaluates to 1. This evaluates to 1. This evaluates to 1. This evaluates to 1. And this evaluates to 0. So the issue is here on this line. Well, what is the circular counter at this point? It's minus 0.6. Why would that be? My from and my to are... Probably shouldn't be calling them from and to, however. I should be calling them minimum and maximum. That's not gonna fix anything. So I am at 1.7 and I add 1.7. What is 1.7 plus 1.7? That's 3.4. Well, let's run this here real quick. If I am trying to wrap the maximum and I am at 3.4 and I am in the range of 1 to 3, what's that? Minus 0.6. So the issue is with the wrapping thing. What version did I just invoke? It was a line of code that looked like this. So this is invoking the maximum function, value 3.4, minimum 1, maximum 3. Is the value less than the maximum? No, it's greater than. So value minus, oh, I forgot some parentheses here. And now everything is passing. The wrapping, the circular counter, everyone is happy. I am very happy with what we have. It's looking great. It's as fast as it can be. It's relatively easy to use. Like it. I really like it. So now we have to write tests for the circular buffer. Don't have anything there yet. It's right after arrays. It's a great place to be. So let me copy the structure of the test. And then I will get rid of all of this. So what do I need to create a circular buffer? I need to pass the size and the number of channels. I'll have a size of 5 and 2 channels. Right. So now I will set some values in there. Let me call the set function. On channel 0, I will pass a value of 1000. And on channel 1, I will pass a value of 1001. Then I will advance the circular buffer. And I have, let's say, 3 positions to make this relatively faster or relatively fewer lines. So next I will do this. I'll do this 4 times. I have a size of 3, so I have position 0, 1, and 2. So this is position 0, position 1, position 2, position 0 again. That's why I'm doing this. Great. So now so my pointer here is where I am writing, not where I am reading. Does that make sense? Oh, even before we consider that, let's revisit this implementation, because now we could be using wrap over here, right? That was what prompted me to extract this in the first place. So what do I need to do? Well, it's just this line here that will change. I will say position equals wrap minimum of position and size. I think that's it. And this whole logic here sounds a lot like the logic for the circular counter, this thing over here. I wonder if I could flip the whole thing around and use the circular counter for that, but I don't think I like it. I think that the circular counter is only for when you're counting up. Yeah, that makes sense. It kind of reads asymmetrically, which isn't too nice, because when you're calculating the position, you're using a circular counter, and when you're calculating the offset, you're using wrap, which is the lower level abstraction, but I think it makes sense. Circular counter is useful in other contexts. And this notion of counting down isn't really useful. So trying to make the circular counter support negative steps isn't too hot of an idea, I don't think. We want this to be as fast as it can. So yeah, this is calculating an offset. So that's why it's asymmetric. This is not gonna pass. I'm not going to advance at the end. That's what I'm gonna do. And then the read head will be in the right location. So then we can start using get. We already tested new and set and advance. So we can start using get and test the values that are in there. And here I am subtracting the offset. I think I should add the offset. I think that the offset should be negative. Right now it's 0 on this one. I expect this to be this. That. And then we'll do this for the 3 positions in the circular buffer. And I expect this to be 2s and this to be 1s. And I will not really test that this is gone. But maybe I should. How do I test that this is going to be overwritten? Guess I won't. Let's see if this is passing. It looks like it is, which is surprising. Well, it is passing. Great. All the implementation was right first try. And then I would like to be able to test that this is overwritten. So how do I do that? There is really no way. Well, yeah, I could always just check this value from here and yeah, I think this is good enough. Circular buffers, they are working, they are multi-channel, they are great. So next step is waveforms. I want to revisit waveforms. So I guess you see where I'm building up to. I am trying to recreate the volume effect that we were using the old library for, trying to get everything that we need for that. So we'll also need the follower, that's already here. So with the waveform display, I think we'll have everything we need to do the volume effect with the new version of the library. So yeah, that's it for now. Tomorrow we'll be back and we'll do waveforms. Yeah, thanks for being here. Thanks for supporting me, subscribing to the channel, all that good stuff. And I see you back here tomorrow. Have a good one. Bye.